In this video, we're going to be talking about Euler angles and rotating reference frames. So the first problem that we're going to be doing is the figure below is a view of the inertial x and inertial y axis. On the figure, draw a sketch of an aircraft and its inertial velocity such that the aircraft position is the origin of the inertial frame. Wind direction is from west to east. The aircraft has a yaw angle of psi equal to negative 60 degrees and phi equal to theta, which is equal to 0 degrees. And the aircraft has a side slip of beta equal to 20 degrees. And draw the top-down view of the aircraft, and the angles have to be to scale. So, before I start drawing the actual sketch with all the complicated details, I just want to hammer out this key idea about how the wind vector affects the velocity of the aircraft with respect to the inertial frame and the body frame. So we've got this aircraft here with the body and inertial frame aligned. And this is a situation where the wind does not equal 0, so the wind affects the air velocity, the air relative velocity of the aircraft. So we see that since there is wind, we've got this beta side slip angle, and we've got the inertial velocity there, and the air relative velocity right there. That's psi equals 0, and there's wind. And in this coordinate frame, we've got psi equal to 0 again, so there's no rotation about the z-axis, and we do have wind, or we do not have wind. So beta equals 0, and the air relative velocity is equal to the inertial velocity. And that inertial velocity can be expressed in any frame. It can be expressed in the body frame, the inertial frame, but the key idea is that when there's no wind, they're the same vector, and they point out the nose. Okay, so now we've got this aircraft, and it does experience a rotation about the z-axis. So it experiences a negative 60 degree rotation. So those are our new body fixed coordinates. And there's wind, so we have this beta angle of 20 degrees. And that is the velocity expressed in the body frame. And this wind vector is pointing from west to east. And that's the inertial velocity expressed in the body frame. But they want us to also sketch the body x component of the inertial velocity, UE. So we just project that onto the body frame, and we've got U, EB, and VEB. Defined in the inertial frame, expressed in the body frame. Problem number 2. The novice pilot is back. Instead of manning the aircraft today, he decides to run and jump around the cabin. He starts in the cockpit at time equals 0, which is fixed at this location, relative to the aircraft coordinate frame. And his position relative to the cockpit in the body frame is given by this vector, and the aircraft's inertial position in body coordinates is given by this vector. However, since the pilot abandoned the cockpit, the aircraft is making unexpected motions, and the orientation of the aircraft is given by these Euler angles. Part A asks us to sketch and label vectors that represent the positions of the pilot relative to the cockpit. So that this vector is the orange vector that I underlined earlier, the cockpit relative to the inertial coordinate frame, which is pink. We'll label that. They did not give us that. And the aircraft and the pilot relative to the inertial frame. We are only given the aircraft relative to the inertial frame. And you'll see in part B that they want us to actually find the position of the pilot relative to the inertial frame, which we will need all of the following vectors to do so. And part C is what is the inertial angular velocity of the aircraft in body frame at t equals 2 seconds. So let's just make a note of what we're trying to find so that we don't forget which frames we're trying to rotate into later. Because they only gave us vectors in the body frame, eventually we will need to rotate that vector into the inertial frame because that's what they're asking for in part B. Okay, so for part A, I'm just drawing the inertial frame right here, FE. And this is the body of the plane. And the pilot is not in the cockpit, which is the square right there. So this is the body fixed frame that I'm drawing right here. Labeling the cockpit, and the y-axis is out the right wing, as usual. This is the position of the pilot, expressed in the body frame and defined in the inertial frame. So that's what we're trying to find in part B. And the pilot relative to the cockpit is this vector. And this purple vector right here is the cockpit relative to the aircraft, expressed in body frame coordinates. And they didn't ask us to draw that, but it's useful in the future when we're trying to do some vector addition. The brown vector is the aircraft relative to the inertial frame, and the pink one is the cockpit relative to the inertial coordinate frame. So using vector addition, it's super easy to define the position of the pilot defined in the inertial frame, expressed in the body frame. So we'll just call that blue, even though it's not expressed in the right frame, we'll just rotate it later. So if you add the orange and the pink vectors, you get the blue vector. And they gave us the position of the pilot relative to the cockpit, expressed in the body frame, and it's at 1 second, so let's just plug in 1 to t. And that equals that vector. And we can do some more vector addition for this pink vector. We can add the purple vector and the brown vector to get the pink vector. So that's the cockpit relative to the aircraft expressed in the body frame, and the aircraft relative to the inertial frame expressed in the body frame. And I just labeled those colors right there, and they gave us those things so that we can find what the position of the cockpit relative to the inertial frame expressed in the body frame is based off of those vectors. That's why it was helpful to draw the purple vector even though they didn't ask for it. So that's what the position vector is expressed in the body frame. So just adding the pink vector and the orange vector together, the two things we just found, we get this vector, which is very close to what we're looking for, but it's expressed in the wrong frame. They want the inertial frame, so we need to rotate it. It's a very easy detail to miss. So you just multiply the vector that we just found by the rotation matrix from frame B to frame E. And at 1 second, we can just plug in 1 to t, and our angles are as follows. The rotation matrix from the body frame to the inertial frame is the transpose of the inertial frame to the body frame because it's an orthogonal matrix. So let's just take the transpose of that. And this is the MATLAB code. So just defining our angles right there and making a vector for the angles so that we can plug it into this function that I have written somewhere else. For the rotation matrix, Q is just it's different notation for it. And then we have our position vector that we're trying to rotate into a different frame, and that's what it is right there. And the multiplication of it is right there. And that matrix math gives us this vector, which is what they asked for. So does this answer make sense? Well, at first you might say, no, it doesn't make sense. Why is the position in the inertial frame the same as the position in the body frame? Well, if you think about it and use the Euler angles to describe the orientation of the plane before and after the transformation from one frame to the other, it starts to make a little bit more sense. So let's take this plane, and the x-axis points out the nose of the aircraft, the z-axis points down, and the y-axis points out the right wing. And we know that due to the right-hand rule. So the first rotation we need to make is about the z-axis, the yaw, about psi degrees. And they gave us psi equal to pi t, and it's at 1 second, so it's just pi. So we need to make a rotation pi. So now this is what the aircraft looks like after the 3 rotation. So we go 3, 2, 1 in that order. And now the second rotation is about the theta. So theta equals pi in this example. And we need to rotate about the y-axis. And that's out the plane, so wings. So we need to rotate pi about the y-axis. And then we need to make our last rotation about the x-axis, which is here, pi degrees. And you see that the plane is in the same orientation as it was before. So since the orientation in the body frame is the same as the orientation in the position in the inertial frame, it makes sense that our position vector is the same in both frames. Finally, we need to find the inertial angular velocity of the aircraft in the body frame at time equals to 2 seconds. So we know the angular velocity has components p, q, r. And we can relate the Euler angles to the Euler angle rates with this equation. And what I'm about to write is wrong. Phi dot is actually pi, theta dot's 0, and psi dot is 0 also, because we take the derivatives of the Euler angles that they gave us, which was pi t, pi, and pi. So now just plugging it into MATLAB, with those Euler angles that I just underlined, we get pi 0, 0. And this is radians per second. The last problem. 2 aircraft are flying side by side. Body coordinate frame A is centered on the left aircraft, and body coordinate frame B is centered on the right aircraft. The coordinate frames have roll, pitch, yaw axes defined by these vectors, and the coordinate frames are initially aligned. Aircraft A observes a third aircraft C in the distance and moves to intercept it at t equals 0. The constant 3, 2, 1 Euler angle rates of the coordinate frame A relative to the coordinate frame B are these Euler angle rates. What is the angular velocity of A with respect to B expressed in the A frame at 2 seconds? Let's just draw a diagram depicting the angles and the directions that they are turning about these axes. And we need this relation to relate the Euler angles and the rates to find the angular velocity. So we know that time equals 2 seconds, theta equals 0.6, psi equals to -8, and phi equals to -4. And just plugging that into that equation, we know the Euler angles, and we know their rates. and we know time. So multiplying the Euler rates by this matrix right here, we get the angular velocity of the frame A relative to frame B expressed in the frame A coordinates. The notation on this one is a little bit funky, so you have to pay attention to it. While in pursuit, aircraft A observes aircraft C at position, that vector, at time t seconds. This is the position vector of the aircraft C relative to aircraft A, expressed in A frame coordinates, components. The time derivative of this position vector relative to A is this. What is the time derivative of the same position vector relative to aircraft B? In this notion, the superscript to the left of the time derivative indicates the frame at which the derivative is being taken. So in part A, we found the angular velocity of A with respect to B. So that means the A frame is rotating. So we can't just take the derivative of the position vectors of frame A. We have to use the transport theorem because frame A is rotating with respect to B. That's frame C's position vector with respect to A, and that's in meters at 2 seconds. They also gave us the velocity of frame C relative to frame A expressed in A frame coordinates. And this is the body frame of A, so we can use UVW, and the components are dotted. We want the derivative of the position vector with respect to frame B. So we can use the transport theorem for that. The derivative of the components plus the contribution of the rotation of the frame. We know this because we found that in part A. That's contribution due to the rotating frame. And since we know what U dot V dot W dot is, and we know what the angular velocity vector is from part A, we also know the position vector expressed in A frame, and this is in meters. We can find the position vector of aircraft C with respect to A expressed in A frame taken by the derivative with respect to the B frame. And it gives us this vector. Thanks for watching, and subscribe for more solutions to these difficult but very interesting problems.